Hello everybody, welcome back to our calculus course. Well, hopefully you have reviewed what we have discussed last time about the L'Hospital's rule to help us to calculate, those 7 complex limit forms. So in today's lecture, we're going to show you more tools to calculate, the 7 forms. Okay, so let's begin. Alright, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists, a positive number n. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0. And the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than n, which means the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have this function f(x). Okay, so it means if we have a limit here, like this one is called a, okay, it's called a, around at the point x0. So it means if we choose the neighborhood of x0, right, defined by the formula here, okay, this is like x0 minus delta, this is like x0 plus delta. So in this region, now we have the f(x) in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, it is correct, because on this point it is 5, on this point is 7, now on this point is even lower than 5. So we can say that the function's value is also within a certain range. So we can say it is locally bounded. Locally bounded. Okay, so how can we prove this? Function graph, right? Okay, for the cosine x. So this is basically cosine x. But if we consider the minus sign before it, we can convert it to something like this. Okay, so this is the minus cosine x. If we further change it to 1 minus cosine x, we just have to move this whole function up for 1 unit. So finally we will get something like this. Something like this. This is 2. Okay, so basically you can see in this area it's very similar to the quadratic function, or more generously the second order function, which looks like this, right? This is quadratic function, and this is our minus cosine x. Okay, so in this part, when x is approaching to 0, they look very similar. So that's why we can convert it to this complex 1 minus cosine x to 1 over 2 x squared. So this one you can see here, I put a star here, so please remember it if you really want to enhance your calculation speed. So for many students, maybe you're in the first year of your calculus class, so maybe your teacher or professor is give you the examination, in which a lot of questions will be asked. So you need to speed it up. And also for some PhD students in different majors, so they are taking their statistics classes, or in their major, they have to use calculus to find out the solution of the complex equations or formulas. So many students ask me how to speed up your calculation speed. So this form is very important. It can help us to find out the limit quicker, because we can always simplify our function to something very much simpler, like x or x squared, And this one is very special. I think it's gonna take you for a little while for you to remember. So still the same thing. Write down what I wrote here and try to remember what is shown here exactly. Okay? So in today's homework, okay, so let's think about this question here. Following this lecture, we're going to talk about how to implement this form, this equivalent infinitesimal to find out the limits more efficiently. So for example, in the first group, now, out of the 7 forms, we have the 3 forms listed here: 0 over 0, infinity over infinity, infinity times 0. Okay, so here's one specific example. Now you can see that, of course, when the x is approaching to 0, now we can see tan x is going to be 0. So on top we have 1 minus, okay, sin x is going to be 0 too. So we have 1 here too, and we have 0 here on the bottom, and we have 1 plus 0 squared, and then minus 0. So of course we're gonna have 0 over 0. So that's the challenge. Yeah, we have been mentioning over and over again. So here we go again. So you can see that this is a 0 over 0 type of limit. So you can think about it. Shall we use the Beddoes rule we introduced last time, or shall we use something else? Maybe the table here? Okay, think about it. We'll resolve this problem next time.